I'm going to speak from a slightly different point of view about similar ideas. So what I'd like to do during this talk is to provide a view of these deep network theory. As we all know, these architecture, which are a succession of linear convolutions and nonlinearities, such as linear rectifying units, they provide, in particular for classification or even regression, surprisingly good generalization properties, but basically it's not understood. It's not understood, and at the same time, there has been a lot of numerical experiments on these structures. And one thing that we see is that when you go towards the deeper layers, the different classes have a tendency to concentrate and separate at the same time, so that at the end you can do a simple linear classification and get a good accuracy on the class labeling. Now, the fact that we don't understand how these machines work is now a real issue in terms of robustness validations in critical applications, particularly for transport, medicine, but also in science. I mean, to try to validate the results when you don't understand the estimators is a difficult task. So at the same time, the reason why I think the topic is beautiful is that it's a real opportunity for doing new math and science theories. And that's why I'd like to first do an announcement. We'll be organizing a working seminar on this topic with also outside university collaborators and essentially all the centers within Flatiron who want to participate, with Joanne Brunner. And it will be on Tuesdays from 11 to 12. We'll begin in November 12th with a talk of David Donahoe, probably on this idea of neural collapse that he has been developing, precisely about this, the fact that you see this concentration phenomena happening. So let me begin a bit like Dave by first looking at the deepest layers, which are over there just before the classification. So you have a representation that I call here phi of x, and then you have your linear classification, which basically projects phi of x over a different vector beta y here, and you take the largest amplitude in a product. So basically, your classification is only going to depend upon the orthogonal projection of your descriptor of a relatively low dimensional space, whose dimension is the number of classes here. And you're going to be able to separate the different classes if they are separated within this space. So another way to view it is that you can look at the centroid of each projection of each class over there in the space. And what you want is that the different centroids mu y here are sufficiently separated relatively to the covariance of the class around this centroid. So this can be measured by what is called the Fisher ratio, which is basically the variance of the different centroids over there divided or renormalized by the within class variability, which is average here. So one of the beautiful results that was obtained by Vardan and Donahoe and their collaborators is the fact that as the training goes, when you have deep layers, you see a kind of neural collapse, which means that the variants have a tendency to go almost to zeros, and the class appears to be very well separated on the training data. So the question I'll be asking here is, what kind of mechanism, how can you construct such a phi of x which achieves this separation and concentration phenomena? So the main issue here is that we are in high dimension, and there is a priori a huge variability within each of the classes. So if you begin on the original data here, for example, an image in high dimension, what you would like to do is to reduce variance. Now, in statistics, there is, when you need to estimate a mean with a very high variance, there is a basic approach that was introduced by Stein, which consists in trying to shrink the amplitude of the coefficient in order to reduce the variance. Now, in what direction are you going to shrink? What you can do is decompose the data with a tight frame, like was mentioned by Marie-Lou. So for example, wavelets or any other things. And then each of the coefficients within your tight frame, you're going to contract it. So with a nonlinear, potentially contraction. And if you do that, since the tight frame respects the Euclidean norm, you're going to get a contractive operator. So what kind of contraction? Well, one of the celebrated contraction is the soft thresholding that was mentioned also by Marie-Lou for noise removal, where basically you preserve the sign, but you shrink the amplitude of each of the coefficients. Now, in deep network, we rather use linear rectifiers. And we're going to see that they have a much more subtle behavior because they both shrink the amplitude, but also the sign. Now, in all what I'm going to do here, the bias B0 is going to be fixed one for all. So then you apply a classifier and you basically get a two-layer network, but the operator here is a tight frame and there is no bias in this network. So it doesn't satisfy any universal approximation theory and or such theorems. So all this work, I should say, is the work of John Zarka and Florentin Gut, who are two PhD students in France. Now, if you apply that on standard image classification, such as MNIST that was mentioned by Marie-Lou, or CIFAR images, which are a bit more complicated, what you observe is the following. If you first do the linear classification directly on the raw data, the error is large in both cases, very large for CIFAR, and you observe that the Fisher ratio, which is here, is not so large. When you apply contraction that you learn with a stochastic gradient optimization, so you're going to learn the tight frame, and then you apply soft thresholding, the Fisher ratio, as expected, is going to increase a lot because you reduce the variance, and the classification error decreased by an important factor. And it's about the same result that you get if you use a relu. Now, if you do that same on CIFAR, then same phenomena, the error reduced by about a factor 2, but a relu is much better than a soft thresholding here. So you see that the nonlinearity here plays a role. So what can you say about soft thresholding? Soft thresholding, they are the result of Donahoe and Johnstone, who show that if the frame provides a sparse representation, then basically they are going to preserve the class means, but they can considerably reduce the variance, and therefore they can improve your Fisher ratio. A relu is going to behave in a different way because it can also modify the class means, and I'm going to show that. Now, what about the dictionary? The dictionary, if you look at the type of dictionaries which are learned for CIFAR, you obtain these typical dictionaries for first layer networks, which are oscillating functions, looking a bit like local Fourier or wavelet elements. So maybe the first question to address all that is, do we really need to learn these tight frame F, or can we derive them from prior information? Now, to try to attack these kind of problems, I'm first going to back up a little bit and look at these issues of concentration in statistical physics for a somewhat simpler problem, but still pretty difficult, which is the issue of modeling non-Gaussian processes, in particular turbulence. And what we are going to see is that here the wavelets come very naturally. The relu come also very naturally to separate scale orientations and phases. Then I'm going to go back to image classification. And first I'm going to try to see how far we can go without learning, basically using this prior, and then go back to learning and see exactly what do we need to learn in order to reach state-of-the-art results. And the main thing is that we'll see we only need to learn transformations along channels. Okay, so let me go back to standard models in statistical physics. So in statistical physics, when you want to build a model, you are going to compute observable, which is basically a vector of statistics, such as temperature, pressure, And what you hope is that your system is big enough so that you have a concentration phenomena happening. Basically, your statistics are going to stay very close to their expected value if the size of the system is big enough. What that means is that if you take one particular realization, x0, first of all, this concentration means that if I take all the typical realization, if I map them with S, they are going to be concentrated in a very small ball. Now, if I take any x0 typical realization, it's going to be, of course, mapped very close to the mean with a high probability. Now, how can you build a model? Now you can consider the set of all possible data elements whose statistics are going to be close to the statistics of the particular x0. And you can now build a maximum entropy model, which is basically has a maximum entropy and therefore has a uniform distribution over this set because it's bound. And that provides you a model of the true distribution. You can sample this model, and let's say the simple computational way to do that is to begin from white noise and then do a stochastic gradient descent in order to recover the statistics of x0 that was in particular studied with Johann Brunner, which will not get an exactly maximum entropy process, but will be for this talk good enough. Okay, so the question we are facing here is how to build these statistics in order to have a good model. What is a good model? It means that your microcanonical ensemble here should be close to the true typical realization. Okay, let's begin from simple problem, Gaussian models. So the only thing I know here is that I have a stationary process. So the probability distribution is invariant to translation. So it's going to be characterized by its covariance, and I'm going to compute here the empirical covariance to translation, which concentrates because it's stationary and I average in space. Good. So here's my true probability distribution. That's basically the principal axes that are going to be reproduced by the Gaussian model. If I do that on a fluid, here I have exactly the same second order moments. That's the Gaussian model. And you can see, obviously, you've lost a lot of structure. This is the same thing for a gas. So how can you check that you have an error? You can project your distribution along a particular vector W and look at the marginal. If the marginal is different from the marginal of a Gaussian, that means somewhere you have an error. In particular, if the marginal here is very sparse, obviously, you don't have a Gaussian process. Now, why harmonic analysis? Because if you look at the principal axis, basically because you are stationary, it's going to be given by Fourier transform. And here you are in the world of harmonic analysis. So if you want to build a representation which is sparse, Marie-Lou spoke about it, one strategy is to use localized wavelet filters. I'm going to use here wavelet filters with two phases, even and odd. Each wavelet is going to be scaled. This is the scaling factor, but is also going to be rotated. This is the rotation theta. So you see you have a whole family of wavelets scaled and rotated. And here, same with a different phase. Now, what a wavelet transform is going to do is basically do a separation across all angled scales and phase and compute these coefficients at different, which basically is a convolution at different locations. Now, one thing that you can easily verify is that if your process is stationary, these coefficients are all uncorrelated if you look at different channels, because the wavelets corresponds to different frequency bands. So let's look at an example. Here you have an image. You can compute the wavelet transform with a series of filter banks, the first one, the second one. These filters are tight frame. You are obtaining a representation which is sparse. All coefficients are gray, nearly zeros besides the edges. But if that's a realization of a stationary process, despite the fact that they are apparently very related across scale, they are totally uncorrelated because of the variation of sign. So one issue in physics and math is to understand how to capture this dependence across scales, angle, and phase. And one way to do it is to use a ReLU, and that's the work of Cixin Zhang. Basically, if you apply a linear rectifier on each of the wavelet coefficients, now they are going to become positive. So obviously, they are now going to be correlated. And you can compute at any given position the correlation across all scales, angle, and phase. And you are going to get an empirical correlation matrix. And if you average, this statistics is going to concentrate. Basically, the size of this matrix is of the order of log d squared. Now, given one observation, you can make a maximum entropy model. And if you sample it, that's the kind of realization that you get. And you see here that you're able to capture, at least visually, excellent images which reproduce basically the core structure. And in particular, it reproduces the alignment of phases, the structure. Now, this was a work that we carried here with CCM, with Erwan Alice, Thierry Marchand, and in collaboration with Shirley Ho, to try to apply that kind of thing to model cosmological density fields of matter in the universe. And if you look at the realization of a maximum entropy generation just obtained from these moments, you get not only images which are very good, but it does reproduce the higher order moments as much as we checked, and it gets very good regression of the cosmological parameters. So we see here, ReLU is very natural to build up correlations across scales and angles. Okay, let's go back to image classification. A deep net progressively separates and concentrates. Can we do that without learning? And if we cannot, what do we need to learn? These are the core questions. Okay, let me take a realization here in 1D of a random process. As I said, if you want to concentrate, basically you will need to average. The problem is that if you average, you're losing basically all the information about X. So what you can do is recover the high frequencies with a wavelet convolution, and you are going to get your high frequencies here. The problem is that if you want to get something which described X, which again concentrate, you cannot average, otherwise you are going to get 0. So same strategy as before. Let's apply a ReLU, which removes the sign, and then you can average. And now your value is going to concentrate, and you are going to get a statistics which is going to be reliable. Of course, because you averaged, you lost information. How can you recover the information? The information is in the high frequencies that you've eliminated here. Where are the high frequencies? You can capture them with wavelets. And if you, again, need to concentrate these values, you are going to apply a ReLU and average. So what are you doing? First, you apply your wavelet filter, your rectifier. This is a frame contraction. Then you iterate, you reapply your wavelet filter and the nonlinearity, which is here a ReLU with no bias. You iterate, and at the end, you are going to do that J time, and you obtain what we call the wavelet scattering networks, because basically it scatters the information across all angles, scales, and phase. It creates many, many channels, but there is no interaction between these channels, which are here. It's basically a convolution tree. It's not a network. Okay, if you apply that for image classification, here's what you get. MNIST with a scattering network like that, to which you just apply, after applying all your layers, your linear classifier, you get the same kind of results as a deep net, because it's a very simple problem. If you do that on CIFAR, the error is 23%, whereas on deep nets, they are much lower, 8%. If you now apply that on ImageNet, which are much bigger images, the error is 50%, whereas LXNet or ResNet goes down to 10%. So basically the error is much bigger. And the question is, okay, what is learned? How come we can't achieve that kind of result? So the immediate idea, and that's again the work of John Zarka and Florentin, is to say, okay, we applied this network, but there's still too much variability. So what you can do is to reduce this variability by applying a tight frame contraction along the channels. So first I'm going to apply a concentration operator, which is orthogonal, which is going to reduce the number of channels. And then I'm going to apply a straight tight frame thresholding, as it was developed by Donohoe and Johnstone, to reduce variability. And finally, a classification. Okay, what does it give if you now learn all these orthogonal operators? On CIFA, you reduce basically the error by a factor 2. You're still not at ResNet level, but you are getting closer. And ImageNet again by a factor 2, and you see how the Fisher ratio increase, which means that you indeed preserve the separation of the means, but you reduce the variance. Okay, how to get the last step? The immediate idea that comes to mind is to say, okay, instead of doing that at the end, why not doing it at each layer? So at each stage, I'm going to apply these wavelet filters, which are spatial convolution and which with the ReLU, which does a shrinking of the sign. And then along the channels, we're going to apply a 1-1 convolution, which basically, as I mentioned, does an orthogonal concentration which reduces the number of channels, and then makes a soft thresholding. So basically, you reduce variability along the channel. This is my operator, and it's going to begin to concentrate the information. And then you separate again with the same wavelet operator, which separates scales, orientation phase, and you concentrate again along the channel. The number of channel increases, 512, and it stays 512 as in standard network. At the end, you get your representation and you apply a linear classifier. So that's the idea. Basically, it's like in a scattering, but now you concentrate along the channel. So that's again the work of John and Florentin. You basically obtain a network which has no bias inside. All the operators are tight frames or at least semi-orthogonal operators. You don't learn the filter in space. They are just wavelets. You only learn the filters, which are these tight frame, along the channels, and you do a thresholding. If you do that, on CIFA, you reach the ResNet 18 performance. So the error is now 7.8%. You see how the Fisher ratio increased by a factor 2 compared to a single contraction if you had applied it on the scattering transform. And the number of layers is much fewer than the ResNet. If you apply that on ImageNet, right now we are at 13% error, whereas ResNet is 11%. The errors are decreasing every day. We'll see if we reach the ResNet. But the point is you are of the same order. And again, the Fisher ratio increased by the factor 2, which explains why you improve your performance. And the depth is small. Now, the question now is how to control this Fisher ratio. We now have a network which is completely structured. No learning in space, just separation of scales. Along the channels, we have an operator which is relatively standard in math, which is a soft thresholding in a tight frame. But you have to control these Fisher ratios. And that's not such an easy thing. At least right now, it's a very interesting open problem. If we can, then we'll begin to understand really how to control the robustness of these networks. So, conclusion. One of the nice observation again on these networks is this concentration and separation mechanism, which is really quite impressive because it shows when, in particular, you have an over-parameterized network that was shown again by Papien, Vardan, and Donohoe, that the concentration on the training is very impressive. So basically what I've been trying to show here is that you can get that kind of mechanism by reducing variance with relatively standard mathematical operators, which are tight frame compression. The second point is spatial filtering doesn't need to be learned. Basically, it's totally controlled by the geometry of the problem. And in this case, the wavelet will do the job. They are able to separate the parameters of the important groups, which are here scales, angles, and phase. So basically, the learning is reduced just along the channel. And there are very interesting questions about what kind of type frame are being learned here. But the point is that you basically reach ResNet accuracy just by learning these elements. So again, the mathematical problem here is how to get upper and lower bounds on the evolution of these Fisher ratio, which is at least for us totally open at that point. So that's it. There are some publication around that, in particular around the cosmological work that was done with Shirley and Erwan Alice, and the rest is under open review. So thanks very much.